this example, I'm going to look at what the distribution of a sum of exponential random variables becomes. So I have some random variables which I call xi, which are distributed as according to lambda e to the power of minus lambda xi, and then I go from 1 to n, and then I write iid, meaning that these are identical and independently distributed. Then I define another random variable y, which is equal to the sum of I from 1 to n of the xi. And then, since this is an example of adding together independent random variables, and now I can use generating functions to find out what the sum becomes. So then I'm going to start with finding the generating function of every single x. And then to do that, I must solve an integral. So in principle, it's this integral, e to the power of sx. Use my new notation, f of x dx goes from minus infinity to plus infinity, but we know that this distribution is only defined for x greater than 0 or greater than or equal to 0. So the integral I actually have to solve is this integral. And that's a straightforward integral to solve. It becomes lambda over lambda minus s. So now we have expressed the moment generating function of an exponential random variable as a rational function in S. And now, since the y, moment generating function of y, is supposed to be just a product of such terms, it becomes simply this. It's lambda divided by lambda minus s to the power of n. So what could this be? Well, I've said that the exponential distribution is a special case of the gamma distribution. So perhaps we should take a look at the moment generating function for the gamma distribution then. What do we get then? So let us just spell it out. We find an expression for the gamma distribution in a textbook or Wikipedia or whatever you want to look. So here we have those constants in front of it. Again, we are only going from 0 and upwards. So it should be x and e, but then I have exponential. So I have x divided by theta, and in addition I just have this x and s term, which I just put together in that parenthesis. So what does this become? Solve this integral, then I have my constant there. And then when I solve it, I use my tables of special function integrals, so definite integrals of exponential and rational functions, and I will find something like this. Okay, those two gamma functions of k, they cancel against each other. And this one I can put in here, see theta power of k. I have something power of k here, so I can just put it right inside. Okay, and now if I look at this thing, this is the moment generating function of a gamma distributed random variable. You see that it's very similar to this thing. So then I basically shown that the sum of exponentials must be gamma distributed. So this is of the same form as NYS. If 1 divided by theta, which I have here, is the same as lambda. And then it follows that y gamma distributed, parameters n, and 1 divided by gamma in the usual shape scale parameterization. So then we know what the distribution of a sum of exponentials is.